day at the office. Gotta scope out the suspects. We've got 2 soil types, we could have done it, and we're gonna measure the coefficient of permeability for the constant head and falling head. We've got all the information on them here. We're ready.
Today we are doing 2 permeability tests, the constant head and the falling head tests. We will measure the flow of water through 2 soil samples in order to estimate the coefficient of permeability for each sample. We will be using 2 different soil types for each test. Closely examining our suspects show that the grain size distribution is a little different. This is because the constant head tests and the falling head tests are more appropriate for different kinds of granular soil. Think about why that is.
We also have a towel, our lab data sheet and pencil, a thermometer, a tape measure, a stopwatch, a large graduated cylinder, a small graduated cylinder, tap water, a soil sample in a small cell for the falling head test, and one in a large cell for the constant head test.
It's really hard to set up the soil samples to mimic field conditions because of the disturbance of the soil particles and the flow path. Also, the soil interface with the sample cell wall can impact the measurements. We'll be using soil types that are typically used for constant head and falling head tests, which are a little different.
Today I am joined by Heba and John to run this lab test.
First, I'll turn on the water supply to the constant head test. The water goes from this pump through this clear hose all the way up to the constant head reservoir. From this reservoir, the water can be directed to the discharge and to the soil sample. I'll climb up the ladder to show you the constant head reservoir. You can just barely see the ghost bubbles caused by the inflow of water into the tank. You can see that the water maintains the level right at the outflow. This is because the hose leads to the discharge hose and the hose to the sample. We want the water to be able to flow to both sides evenly, so I'll open the valve. You can see that the water goes down this pipe to connect to the constant head sample cell. And you can also see that the head is maintained at this constant level because any excess water is discharged here. We are going to check all the valves before we begin, and right now the valve at the base of the tube and at the inflow into the sample are open. The valve at the outflow from the sample will stay closed. The first step is to bleed the air out from the top of the sample. I'll unscrew the release at the top and we can see that the water begins to bubble out. This sample is already saturated, but we can make sure that there is no air in the hose or the sample. After the air is forced out, we'll close the release and open the outflow valve. The tube should be parallel to the ground so we can properly measure the head. We need to measure the length of the sample, the area of the sample, and the head at which this test is being conducted. We measure the head at the vertical difference between the water level up top and the outflow down below. We need to take and record some measurements of this setup so that we can do the calculations for this lab. The first trial of the constant head test is different from the rest. We use this as a reference. We will fill this large graduated cylinder to 450 milliliters and time how long that takes. The stopwatch will be running in the corner to show the passing of time. As soon as Alyssa says go, I'll put the cylinder into the flow of water and the first trial will begin.
Really gotta put this down because I'm really about to hold it for 3 minutes and 30 seconds, but that's okay.
now!
This trial took 4 minutes and 58 seconds to reach 450 milliliters. I'll record the time on our data sheet and we will measure the temperature of water. We will wait for 2 minutes to make sure that the temperature is exact. Taking the temperature is important because the calculations is based on water at a certain viscosity and we will apply a correction factor based on that. The water in this trial is 20 degrees Celsius, which means that it's the right temperature for this test. Now we can dump the water out, reset the stopwatch, and conduct trial 2.
Reset.
The subsequent trials of this test are done based on time, not volume. We have measured how long it took us to get 450 milliliters. Now we will see how much water we collect in the same time. I'll put the cylinder under the water flow and start the stopwatch and begin trial 2. After 4 minutes and 58 seconds, we can see how much water we have collected. You can see that it's less than 450 milliliters. It looks like it's 395 milliliters in this trial. We'll measure the temperature again and we can see that it's closer to 19.5 degrees Celsius. And we will need to consider the temperature corrections. Do you know if the water has a higher or lower viscosity when the temperature decreases?
Ready, set, go.
Now we will go undercover and watch the water collection in the third trial. We'll measure the volume collected after 4 minutes and 58 seconds again, the temperature of the water, and record these values.
Two, one. Summer down. Alrighty.
You can repeat this test many times, but we are now going to go through the falling head test.
Setting up the falling head test is similar to the constant head test. We will use a smaller graduated cylinder because we'll get much less water, but we can use the same thermometer. The difference between these two tests is in the development and measurement of head. In the constant head test, we saw that the water level was maintained. This is good for granular soil that will let a lot of water through. However, for a less permeable soil, we want a more precise way to measure this, so we'll use the following head test. We measure the water outflow as it falls from H1 to H2. The head difference is the head at H1, which is measured from H1 to the outflow, minus the head at H2, which is measured from H2 to the outflow, and this simplifies to just H1 minus H2. We can move the cell outflow tube against this ruler to measure the heights. The volume of water that goes into the sample Q in is equal to the volume of water in the tube between H1 and H2, and Q out is equal to the volume we get in the graduated cylinder. Before actually running this test, we have to get rid of any air bubbles in the standpipe. We'll pour water into the top to develop the head that we need to get the bubbles out and run the test. Of course, we need to check all the valves before we begin. Sample outflow and the valve at the base of the standpipe should be closed, but the rest can be open. You can see that the bubbles are pretty significant compared to the volume of water between H1 and H2. It's very important in this test. We'll open the valve at the base of the standpoint and bleed out some of the water to get the bubbles out. We don't want the water level to get below the funnel right now, or more bubbles or air pockets will get into the standpipe. We also have to get the bubbles out of the tubing to the cell. We reconnect the cell to the standpipe and let some water flow through to force the bubbles out of the cell. We'll move the tubing around to convince the bubbles to escape. Then, we make sure that the valves are all open and prepared to run the test. This test goes very quickly once the water hits the standpipe because the area of the tubing is so small. As soon as the water level hits H1, Hebo will start the timer and John will put the graduated cylinder into the outflow.
1, 2, 3, start!
We can see that the water level is slowing down as the head decreases. Why do you think that is? When the water level hits H2, Hebo will stop the timer and John will remove the graduated cylinder.
And stop.
You can see that this test is much faster and the volume collected is much less. The temperature for this test is also slightly higher. This is because we are not using fresh water from the faucet, but the water has been sitting out in this container, which is more room temperature. Now we will redo the test for trial 2. For this test, we need to redo the whole process of getting the air out of the standpipe and sample tubing. And now we can get a first-person view of how tall the head is. We have to remember to check the valves each time. And we make sure to let any small bubbles in the standpipe float to the top so they don't mess up our test.
Who do you work for? Who's your contact? We'll get it out of you. This guy's on the run. Police chase. Police chase. You can run, but you can't hide.
Then we can run the second trial of the falling head test. The values are similar to the first trial, and we can run this test many times to try to get consistent results. Permeability is a really important concept in geotechnical engineering. Understanding how well water can flow through a soil can be used to predict how quickly and how much soil will settle underneath a building foundation, which is important to know for differential settlement under buildings. For secondary settlement, granular soils will settle almost immediately, while fine-grained soils will continue to settle over time. Not only does sand typically have a better bearing capacity than silt, but it also has a higher coefficient of permeability. And this means that the settlement after a long time could be differential settlement and cause cracking in the structure. Permeability is also useful for environmental engineers determining how contaminants will move through the environment. It can also be used for site civil or stormwater work in order to design detention ponds, for example. Let's take a look at how we can use a ring infiltrometer test to measure permeability in the field, specifically for detention ponds. This can be done as a constant head or falling head test. In this case study, a falling head test was used. A test pit is dug to the estimated depth of the detention pond based on boring log data. First, like in the lab, we'll use a hose to run water through the soil to make sure it's saturated before we begin. Then, using a ring to contain the water on the surface, we can also use a ruler to measure the head drop over time, at the bottom of this test pit. Detention ponds are used to reduce flooding, so if this rate is too slow, the detention pond will fill up with water very quickly and it won't drain, so the flooding won't be mitigated. For calculations, you'll need to calculate the following values for your report. Please discuss this with your in-person group mates if you have any questions.